I hope you can hear me. Let's wait for 2 to 3 more minutes, then we'll start with the weekly problem solving session. I think we should start now. Yeah. Good evening again. I am Abhinav Sandrakar. I am the TA for this course, Mechanical Behavior of Materials, which is taught by Professor S. Sankaran from IIT Madras. Uh, this is the third week of the problem solving session. Today we'll be firstly completing those assignment questions which we had started last week. Since we were stuck in a few problems, we could not complete it last time. So let's first start with that. Then we'll move into the concepts which were taught in week 3, and then some assignment questions related to the week 3 content. In case there's anything you want to ask, you can ask in between or even now. You may just unmute and ask. So as I tell in every session, feel free to keep your mic unmuted and ask any kinds of question you might be having. It's better to have interactions. Yeah. So let me open the week 2 assignment for the previous year. Here we had solved question number 2. I think we had solved question number 3 also. Uh, hmm. So question numbers 3 to 7 had been solved. I think so. Yeah, so 3 to 7 have been solved already. Question number 1 was not solved. And in 7 we had a doubt, and 8 and 9 to 11 were also left. In case any of you attempted the questions, you can let me know if you know the answers or have solved it. Yeah. So this is answer 3 to 7. Hmm. Sorry, 3 to 6. Okay. So let's look at question 1. We were confused about one earlier. So this is the question. We were given sigma 1, sigma 2, sigma 3 values and tau 1, tau 2, tau 3 values, and had to find out what will be the corresponding Mohr circle for that stress state. So actually the reason we were stuck with this, later I clarified with some uh, people. So I got to know that the reason we were stuck was because we were considering them as the actual stress state, the sigma values and tau values as those of the actual stress state. But you will get the solution if you consider them as the principal stresses and the maximum shear stresses, and that make the problem much more easier to solve. You do not need to solve any cubic equation to find the principal stress, because already the stresses which are given are the principal stresses and the maximum shear stresses. So that makes this very straightforward. How we will approach this now is that you will just make three more circles, two inside one of them. One will be, usually I think sigma 3 is the highest. Oh, yeah, sigma 1 is the highest. That's the convention. So sigma 1, maybe sigma 2 is in between, sigma 3 is the lowest. See, so these are the principal stresses. Similarly, we'll have tau 1 the highest, tau 2 and tau 3. So we have the sigma values and the tau values. Even having just the three principal stress states is enough to define what is the Mohs circle. So let's see, for B, you have sigma equal to 0, sigma 2 equal, sigma 1 0, sigma 2 minus 25, sigma 3 minus 50. And tau is also given. So two of them are negative, one is 0. So since, so this seems to be the one which corresponds to this kind of stress state. Let me, so it will be B. In C you have sigma 1 10, sigma 2 minus 20, sigma 3 minus 50. So this corresponds to number 3. If we look at tau, tau is 30 for one and 15 for the other two. So that also seems to be matching for what we see in option 3. In D you have sigma 2, sigma 3 and sigma 3 equal to minus 10 and sigma 1 equal to 40. What this means that the two circles inside are overlapping with the first one. and that can also be understood as tau 1 equal to 0. So one of the circles is just this one point, and the other two have tau equal to 25. So the whole of this are the other two Mohs circle. So together they are the three Mohs circle for the three reference planes. So this will be pretty straightforward. And so the one where you have all sigma same and tau equal to 0, it will be A. That is hydrostatic loading. So with that, we'll quickly proceed to the next question. We need to finish this and start the week 3 content. I'll appreciate if you share any of the doubts you might be having. So A1, B, B4, C3, A1, B4, C3, D2. That is matching with the answer. So this is also done. Yeah, in question 7, we had already seen that there's a rigid surface. If we, let's say, about the sorry, the YZ plane is rigid. So epsilon x will be 0, epsilon xx. Hmm. Epsilon xx will be 0. There will be some value of epsilon zz since you are compressing, and some value of epsilon yy since due to Poisson's ratio. So this we know for sure that it is plane strain, and because it is plane strain, it cannot be plane stress, because even though epsilon sorry, so we know that sigma mm, z zz is not equal to 0 since we are applying a load. Sigma xx is also not equal to 0 due to the rigid surface which will have a normal force. Then there will also be some tau x z to counter the weight of the block, right? So there will, if you draw the FBD, it will be something like this. There will be shear stresses which will counter the weight of the block. And also there will be likely some shear component in the tau uh, um, shear component which is being exerted by the surface in the y direction. So tau xy will also likely be not 0. There will be some value. And because of that, you'll also have tau yx. So since you have some shear stress on the y plane, this will not be a plane stress condition since you have shear stresses on x, y, z, all three plane. And that's why we can say that it will be plane strain, but not plane stress. Now let's look at question number 8. We have elastic stress tensor given. We have to calculate the total strain in x direction. So we need to basically calculate epsilon x, strain along x, and we know that this will be equal to epsilon xx Mhm. Plus epsilon yy, we'll have to also consider the effect of mhm. Wait. We have been given the elastic stress tensor. We have to calculate strain. So yeah, I was confused a bit. So we know epsilon xx, which we need, will be equal to sigma xx by E, and also the contribution due to Poisson's effect. So plus sigma yy mm, by E into minus of mu plus sigma zz by E into minus of mu so this should be equal to if we just remove 1 by E, here our E value is 210 GPa. If any of you have solved it and know the answer, you can let me know what it is. We can cross check that also. Mu is known as 0.33. Mm, okay, so this will be 1 by 210 GPa into 240 minus 100 into minus mu plus 160 into mu, and this will become mu is 0.33. Let me quickly calculate. I hope you are understanding this approach that we have taken. Getting it as 1.05 into 10 raised to minus 9 into 10 raised to divided by 10 raised to minus 6. So this will become 1.05 into 10 raised to minus 3, and this is option A. So the correct answer is option A here. Now let's proceed to question number 8 to 11. Here we have been given this stress tensor. We have to find the principal stress, sigma 1, sigma 2, and sigma 3. And 20, 0, minus. So we know that sigma minus lambda I equal to 0 needs to be solved, and the values of lambda will give you the principal stress values. So basically you need to find then what is the solution to this cubic equation. Let's see if we can solve this and get some answer. So I think this is they have made this easy for us. So if we open up this matrix, it will be 5 minus lambda into 10 minus lambda into minus 20 minus lambda minus of 20 square equal to 0. So one value is lambda equal to 5. The other values will be 10 minus lambda into 20 plus lambda equal to minus of 20 square equal to minus 400, right? So this is a quadratic equation. We'll have to solve it. Lambda square minus 10 lambda plus 200 equal to minus 400. Lambda square plus 10 lambda minus 600 equal to 0. Now we solve this equation. Minus 10 plus minus root of 700. Sorry, this will not be 700. This will be 2500 by 2 equal to minus 30 comma 20. So our values are 5, minus 30 and 20. But what are our units? Who all are present? So two people are present. So can you tell what will be the units? So in the question it is given that it is kg per mm square. Can we convert it into pascals or megapascals? So Pascal is the SI unit. It should have meter in its formula to make it a SI. So mm square equal to 10 raised to minus 6 meter square. So this lambda is in megapascal, and we can say that the answer will be 30 minus 30, 20, and 5. Let's check. Yeah, it's matching. Now we have been asked what is the maximum shear stress. We can construct the Mohs circle for this. So minus 30, 20, and 5. Maximum is 20, minimum is minus 30. Something like this. Then 1 is at 5. So it will be like this. Sorry, my drawing is not good here, but these are all circles. Just assume. It's 20 minus 30. So the maximum shear stress will be the radius of this. Tau max will be equal to radius. So that will be 50 by 2, diameter by 2 equal to 25. Here it says 26 to 27. This answer is wrong. It should be 25 exactly. But mm, it's fine. Hmm. Maybe if we write it as kg4, okay, it's fine. The answer is 25. The hydrostatic stress component is. So how do you find the hydrostatic stress component? The mean stress, right? Mean normal stress equal to the mean of the mean of the principal stresses, right? Actually, the mean of the principal stresses or the mean of this stress rate all will be the same because sigma m, which is also called J1, the first invariant is equal to sigma I by 3, which will be equal to 10 minus 20 plus pi by 3. So yeah, initially I was confused, but problem solving can help you recall these concepts. Minus pi by 3. How much is minus pi by 3? Ah, 1.6. 1.6777. So minus 1.67 MPa, since we have already calculated. So that is the end of our assignment 2. I'll upload this to the shared drive. Hmm. I'll really appreciate if more people join and ask doubts, interact, but it is fine. So first let's summarize. We'll do a summarization, take a small break, and then we'll start with the assignment 3. I'm not sure if you people are solving assignment 3 or you are solving it in prior, but that will be very helpful for those who are really serious about doing this course well, learning well from this. Hmm. So in week 3, good amount of content was covered. In week 2 we had finished with elasticity. In week 3 we'll start looking at plasticity. But before that, we'll look at some other elasticity and bonding related things. We had already talked about polymers. So polymers have a low elastic modulus when in tension, and it is non-linear. This is, we had discussed it due to chain alignment, which is very easy. So initially when you strain, just the chain alignment occurs. There is no bond stretching as such. So because of that, the modulus is low. After a certain point, there will be bond stretching, and that bond stretching will lead to a higher modulus. But if we look at cellular materials, so materials which have cell kind of structure, it could be either voids inside cells, like vacuum, or some gas inside the cells. So the outside boundary of cell is made of the solid materials, and inside it is empty. So this is a spatial structure of a material, and in these materials we observe that the compression shows a non-linear low elasticity property. And here the reason for this low elastic modulus and non-linearity is attributed to this kind of behavior, that this kind of strain that takes place, and that is buckling of the cell walls. So the shape of the cell walls will change initially when you are compressing, which is called buckling, and that will be easy to do. Once it has buckled to a certain extent, then further compression will lead to uh, compression of the bonds, and the atoms will try to repel that, and due to that you will get a high compressive elastic modulus. But initially it's just the change in the structure, just buckling of the cell wall, and due to that the modulus is low. So I'll try to be quicker. I won't explain all these reasons which sir has already explained. So we again look at the potential energy curve, a very important concept in material science. We had already seen the asymmetry that is there for compression and tension, and this also results into a positive thermal expansion coefficient, which is given by alpha. This is the formula for it. The energy well can tell you a lot about many fundamental properties of the material. So a deep well will correspond to higher sublimation energy, since the bond energy is more. It will also tell you about the thermal expansion coefficient. The shape of the curve has an effect on the thermal expansion coefficient. The modulus will also be high if the well is deep, because mm, the slope is sorry, the curvature is high, right? Modulus is basically stress by strain. So if you apply force, how much is the displacement? That is given by the slope of the F force versus displacement curve, which is the curvature of the energy well. I'm telling it fast because it has already been covered by sir in the course. If you have doubts, you let me know. Then we move to this another interesting concept called anelasticity, which occurs in all material classes but more in polymers. Anelasticity refers to elastic strain dependency on time. So if you this is often seen as a damping effect. So in case of presence of anelasticity, you have a lag in the stress strain curve during lag in the stress and the strain portions. So even if you apply stress, the strain takes time to be applied. It is time dependent. And this especially occurs during relaxation when you have removed the stress. And this is associated with energy loss. This lag is because there is some time required for migration for the different processes which usually involve migration of thermal current, atoms or defects, and each of these have their own time scales of migration or diffusion. So then we look at thermoelastic effect, that is the relationship between elastic deformation and thermal energy. So it is possible that when you load, it can be I don't want to explain the whole thing, I'll just give you a gist of it. So when you load, it can be either that you load it so slow that there is no temperature change. So we call it isotropic. But it can happen that you load it very fast, so fast that there is no time for a thermal exchange. That will be adiabatic. And after that, once you give it some time, it will again come back to the same temperature. So this will be associated with some energy loss. So, and this can be seen from this curve, that as you are going and coming back, there is some difference in the some energy which is given by the area under the stress strain curve, and this is the energy dissipation that is occurring in this cycle. This is because we are doing it at finite values of strain rate. So some adiabatic loading is happening. Hmm. Also another thing, if we sometimes damping is useful, like lots of time you want to have damping. So if you want more damping, you can tune the loading frequency such that your material will show the highest lag between stress and strain. It will absorb lot of energy. So if it is absorbing lot of energy, a lot of energy is losing, it means that the chances of failure of the material is lower. So, and this can happen when the loading frequency is of a similar order to the relaxation processes that are occurring. So in that case, the load more of the energy of loading goes into the relaxation process and you get more damping. Then there were certain relations to show how the strain will change with time during relaxation. That was all about elastic effects, thermoelastic effect and elasticity, different in different materials, how it can manifest. Now we'll come to plastic deformation, and to be able to understand plastic deformation, we'll have to know one of the key actors, one of the key actors which plays a big role in plastic deformation, especially in crystalline materials, that is dislocations. So a dislocation is a one-dimensional defect. It is a line defect. And sir has already explained it, visualized it through images. I won't do that here, but I'll go through some of the key concepts related to dislocations that you need to know and some formulas. Hmm. For those who are from metallurgy background, they might be knowing a bit of it, but for those who are from outside, this might be completely new. And whenever there is some deformation occurring in crystalline material, so it could be either metals, of course, because metallic bonding makes it very easy for dislocations to occur. Can also happen in intermetallics at times. They are also crystalline, but the extent of dislocations in them is lower because the bond energies are very high. So breaking of bonds is very difficult. So now let's go to some concepts related to dislocation. So if we try to theoretically see what will be the energy associated with the breaking of a bond. And the reason we are looking at breaking of bond is because dislocations basically are defects which move by switching of bonds. So between two atoms, the bond breaks and a new bond is formed with the adjacent atom. So breaking and making of bond simultaneously, and as it happens over the material, one particular plane of atoms is in a way able to move uh, from one end of a material to another, and once it reaches the surface, it causes a step on the surface, and that is considered as a strain or a plastic deformation. So in this way, by switching of bonds, dislocations travel through the material, and once they reach the surface, they lead to strain, some deformation of the material. Now, if we want to look at how much energy is required in the movement or dislocation, Mhm. So, firstly, we'll just see in case we do not have dislocations, we have a perfect crystal, and the whole layer has to move, a whole layer of at across the boundary layer, the atoms have to move. Maybe let me show here. Talking, like explaining just verbally is difficult. So you have a crystal, you apply shear stress, and it deforms to something like this. If all the bonds break together in this region, then that will require some amount of stress to break the bonds across a whole plane. And if we calculate it, sir has already done that. We try to calculate what will be the relation between the bond strength and the energy required, force required to break it. The theoretical strength of the crystal comes out to be very high in GPS, but actual measured value of yield stresses is in megapascals, maybe 100, 150, 500 megapascals. So, how do we explain this? This can be explained through presence of defects in the material, which can ease the deformation process. And if this defects like dislocations, which are line defects, are present, then the material need not undergo a breakage of all the atomic bonds of a layer. Just along one line, that bonds can break, and this dislocation line where the bonds are switching can move across the plane, which is called the slip plane, and that can also lead to strain. So there you require much lesser forces for the deformation to occur. Now that we have seen that dislocations can cause deformation, let's go more into details of dislocation. So When you need to specify a dislocation's details, you need to tell about it dislocation, its dislocation line direction. What is the direction of the line? The glide plane, the plane on which the dislocation is moving or slipping, and the Burgers vector of the dislocation, the direction in which the dislocation will move. The dislocation can be of two characters, edge or screw. So any dislocation will have a mixture of these two characters only. There cannot be anything else, because these two types of dislocations can lead to all kinds of movements in the sample. So nothing more is required. In case of edge dislocation, you will have a linear displacement. So this is very easy to visualize edge dislocation. This is how we usually represent dislocations also, because it's easier to visualize. But in case of a screw, you have a helical displacement. Sir has explained how it is. So when the screw dislocation is moving, the deformation which is occurring around the dislocation core, it will have a helical nature. So once the dislocation, um, so one dislocation will cause one atomic displacement, one bond length of displacement, and it will be of helical nature. So if you see the image, you can visualize this better. We can also have mixed dislocation having both characters. Then some more salient points about dislocations. The Burgers vector of a dislocation will always be fixed, no matter what its character is, whether it is at somewhere, screw somewhere else. It will always be fixed even for a loop. And the Burgers vector basically, as I told earlier, tells what is the direction of the movement of the dislocation. And whichever direction this dislocation is moving in that direction, we'll observe strain also, because strain or plastic strain is due to dislocations moving to the surface. So that tells about the strain relationship between B and strain direction. Now, as I said, dislocations had been hypothesized long ago, even before we had the sophisticated instruments to look at them at a nanometric level, in nanometer length scale. But this was first experimentally seen through TEM, which is the most common method of seeing dislocations, transmission electron microscopy. Now coming to energy of dislocations. So dislocations are thermodynamically unstable, but they are thermodynamically unstable, so they will always try to annihilate and disappear if uh, the if the kinetics allow for it. So if the energy of a dislocation is higher, it means that it's much more favorable for it to get annihilated. But in general, we will always see dislocations in a material, because uh, there are always some equilibrium number of dislocations at any temperature, due to increase in entropy as you have more defects in the material. So you do expect to have some equilibrium number of dislocations. Mm. But they will correspond to a higher energy. Now let's look at what are the energies. So they can be calculated as being proportional to GB square, of Burgers vector, and proportional to shear modulus. This is the screw dislocation. For edge, you will have 1 minus mu term in the bottom, which will mean edge dislocation has about 50% more energy compared to the screw dislocation, because mu is usually around 0.33, so 50% more energy. And dislocation, since it is a line, this energy can be understood as a line tension. Now coming to how are screw and edge dislocations different, they have different energies of course, but another thing is the stresses around both dislocations will be different because they both have a different geometry. In case of screw dislocation, it is purely shear stress all around it, no hydrostatic stress. Edge has both hydrostatic and shear stress. In case of edge, which is easier to visualize, as I said, you have an extra plane of atoms above a dislocation or below a dislocation. So wherever you have the extra plane, so let's say you have a slice of bread. In between, you try to add an additional bread halfway through. So the portion of the bread, the let's say the upper half, where you have the additional bread, that will try to expand, but you have stopping it. So there will be a compressive stress inside. But below it, because there is some but below it comparatively you will have a tensile stress, since there you do not have the extra plane of atoms. So this is important to understand. Then we look at force on a dislocation. If you apply a shear stress tau, the force will be minus of tau dot b. The force of one screw dislocation on another will be minus gb by 2 pi r into b, minus gb1 by 2 pi r into b2. If you have repulsion between two dislocations, that will mean that there is an increase in energy. And if you have a attraction between dislocations, then that will uh, lead to a decrease in energy. Then we'll come to something more called Frank's rule. So if you have a dislocation, it has a particular Burgers vector. And there's something called perfect dislocations and imperfect dislocation. Or so I won't go into details of what these are, but what you can need to understand for now is that a dislocation can dissociate into two dislocations. So if there was a dislocation with a Burgers vector B, so how I have not told, maybe I should just mention now that Burgers vector refers to the amount of displacement which will occur for one switching of bond. So for one displacement of the dislocation line which occurs due to switching of bond, what is the net displacement or net strain? Sorry, the net displacement, and that will be equal to b. It's a vector, so the magnitude tells you the magnitude of the displacement, and the direction will tell you the direction. Now, if dislocation spreads into b1 and b2, this will only be feasible if the energy of the initial dislocation was more than that of the two which it has got split into. Since a lowering of energy is more favorable. So, and we know that energy of dislocation is proportional to square of the Burgers vector. So, if you have b1 plus b2, the initial dislocation Burgers vector magnitude more than those of the sum of initial ones, then this will be favorable. I think this should be the square here, since energy is equal to square of Burgers vector, not the magnitude of Burgers vector. Let me just check it once. Give me uh, just a minute. Yeah, I think it will be like this only. Then we know that the screw dislocation will have only shear stress field around it, but edge will have both hydrostatic and shear. So the interaction between two edge dislocations will be much more complicated compared to that between two screw dislocations. So if we do the computation of the stress due to one edge dislocation on another edge dislocation, we have something like this. So here I have drawn the effect of one edge dislocation that will occur on another one which is nearby. So this is has been explained much more in a very neat diagram in the slides. I have just made a very rough copy of it. So if you have a edge dislocation in the middle like this is your edge dislocation. This is your xy plane. Your z is outside the plane of this paper, and your dislocation line is along z. The Berger's vector is along x. Then if you have a dislocation at some another point with respect to this first dislocation, we can tell whether it will be attracted or repelled by this diagram. This was done by doing some calculations of the force on dislocation nearby. So basically, if it's in this region, it will repel, that is x more than y, magnitude of x more than y. And if it's in the other regions at the top and bottom, it will attract. So what this will result in is that edge dislocations will try to uh, pile up one over the other, and this will lead to lowering of energy. So naturally, the edge dislocations will experience such a force that they will tend to pile up. And because you know that there is compression on the top, tension on the bottom, both of these will somewhat cancel when they are piling up like this, and this will lead to a lowering of energy. So in materials, you will often see that dislocations are piled up and forming certain structures like these. We sometimes call it cell walls or cellular structures. This is due to dislocations piling up. So that was all which was covered in week 3. Next we can move on to the assignments if there are no doubts. So only 2 people have joined today. Mhm. So if there are no doubts, we'll move on to the assignment. We'll solve the assignment. Let me hide all the answers so that we can apply our brains well without trying to fit the solutions to the actual answers. I also have not solved it before, so I want to also solve it without knowing the answers. Okay. Question 5 seems interesting. Hmm. Yeah. Oops. Hmm. So let's take a short break and then we'll resume. Till then, you can try to answer these questions by yourself or just take a break. We'll come back. Hmm. Hello. So let us resume. Let's start with solving assignment 3. The first question is, for a completely adiabatic loading process, the elastic energy dissipated is. So it's a completely adiabatic loading process. We had seen in the lecture that it will be something like this, a very quick loading, almost instantaneous. Let's say this is time, yeah. So stress is applied very quickly, or actually this axis I think should be strain. The stress is applied very quickly, but we do not see much change in strain. So change in strain takes more time, something like this. And when we relax it, again, initially there will be quick relaxation. This is all in the elastic regime only, and then it will slowly come like this. So this can be considered adiabatic. And here you will have some change in temperature. Sorry, adiabatic also will have be associated with change in temperature. Here you will have a heat transfer, heat change. So overall there will be some energy dissipation, but it will not be in the adiabatic part. It will be in the later part. Instead of this, we could also have had the isotropic process where you have a slower loading. So always you have a same temperature, and here also the loading and unloading will be exactly following the same path. So no energy change is associated, just stretching of bonds that occur. Here I should write. So I'm just explaining the things related to it. The answer is straightforward. Adiabatic will have no heat transfer and no energy, elastic energy is dissipated in it because straining takes place over the rest of the portion. So the answer should be 0. There is no energy loss. The next question is, the assertion non-elasticity during tension is commonly observed uh, in cellular materials. Reason: the continuous collapse of primary bonds is the reason behind such non-linearity. We have talked about it at the start of the summarization. Non-elasticity is seen during compression in cellular material. So assertion is wrong. The collapse in the of primary bonds is reason for such non-linearity? No. We know that non-linearity is due to the change in the shape of the cell. So if the it is also called buckling. So if the cells were initially like this, they will somewhat buckle like this. So this can be seen as a change in shape on deformation. And there is no stretching of bonds per se, like some stretching but very low. The major strain is coming due to the change in the structure. So the reason is also wrong. Yes. Next question is the asymptotic approach of elastic strain to its equilibrium value after the application of load is called. So what do we mean by asymptotic approach? At any value of strain, we expect any value of stress, that is application of load, we expect a certain value of strain, which is the elastic strain. And we know sigma E is equal to epsilon E equal to sigma by E, elastic. Hmm. But due to, as I told, certain processes, time dependent processes, the straining is also time dependent. So we see a kind of asymptotic curve. It will be something, if this is the equilibrium value of epsilon, then it will be something like this. So it took at least some finite amount of time, let's call this tau, to reach close to the expected value of strain. And this is, as I said, due to some time dependent processes. Now we have been asked, what is it called? We call it anelasticity. But I think the option here is wrong. Here they have called it elastic after effect. Let me check if that is actually a term, because it's supposed to be an elasticity. That is the definition of an elasticity. Time dependent training. That is a lag between stress and strain. That is what is happening here. Both are similar, so anything is fine. It's just terminology. Let's go to the next question, question 4. The statement is chain polymers exhibit a non-linear Thin polymers exhibit a nonlinear elasticity in tension. Hmm, that is true. During tension, statement 2, during tension, a crystalline material gets heated due to internal friction caused by application of load. Heating is due to internal friction. In a way, it's true, yes. Statement 3, for a uniaxial loading, the change in temperature of a material with strain is directly proportional to the specific heat of the material at constant volume. Change in temperature of a material with strain is directly proportional to the specific heat of the material at constant volume, delta T. Hmm. So this was mentioned in the lectures. I think I had also just written the formula in the summarization. When we discuss an elasticity. Ah, um, okay, it's not, I have not mentioned, but it is in the lectures. So in case of adiabatic process, let me open the notes where I'm writing it. Answer 4. S3. So for adiabatic process, sir has told the equation of temperature change. So dou T by dou epsilon at constant entropy, S refers to entropy, is equal to minus Vm alpha Et by Cv. Adiabatic means heat transfer is not happening. Entropy is constant. So change in temperature is indirectly inversely proportional to Cv. So S3 is wrong. S4 is material with a higher sublimation temperature has a bigger deep in the Cordon-Morse curve. So Cordon-Morse curve is basically the energy well, and a deeper Cordon-Morse curve will mean that the bond energy is larger for the material. So the energy required to cause sublimation, that is break the bonds so that the material converts from a solid to a gas, will be equal to the energy that is has to be supplied to take the atoms to infinity. Or so this was the E versus X curve. The F versus X curve will be something like this. So you will have to pull the atoms with a force equal to this value to take them apart, and the energy associated with the total breakage will be equal to, because finally the energy is zero at infinity, so the energy required will be equal to the depth of the well. So larger the depth, the more the sublimation temperature will be, since higher vibrational energy is required. So S4 is true. Now let's see. We have S1 true, S2 true. Friction causes this energy loss. S1 true, S2 true, S3 is false. We said it should be inverse. S4 is true. I think three matches, option three matches. Let's see. Yes. No, no. It's saying true, false, false, false. Two and four are false, it is saying. I think this answer key is also wrong. We'll have to see. There are incorrect solutions in the answer key many times. So because we are sure that statement 4 has to be true, because deeper well will correspond to higher bond energy, more sublimation temperatures. And also statement 2 will be true because the loss in energy is usually, or heat generation is due to internal friction only. Let's move to the next question. Here you have a non-planar dislocation loop. All the dislocation segments are parallel or perpendicular to the coordinate axis. L2A is a positive edge dislocation. The character of segments C, D, E, F, G are L2A is positive edge. So let's write it like this: positive edge. So the Burgers vector for this will be perpendicular to the line direction. Like that is the definition of a edge dislocation. So B is in this direction as is shown here. Here in the L, we have been asked about, let's do for all the components. So LK will be screw, because the whole dislocation will always have a single Burgers vector. So even this LK component will have Burgers vector in this direction parallel to the dislocation line. So screw. AB will also be screw, screw, screw. All those which are parallel to LA will be edge. Now, um, because we'll see later, a dislocation is a boundary between a slipped and an unslipped region. So this loop that we are seeing, within that the region has slipped, outside it is unslipped. So if this is positive here, LA has positive character, GF, PB and EJ will be negative. Similarly, screws will have one side positive, like maybe LK and HG, and KF and AB will have opposite signs. So positive on one side and negative on the other side. Hmm. So the correct answer here, we don't need to worry about the signs here. So the characters will be CD, screw DE is okay. Here we have not talked about DE. So DE has also the same Burgess vector and it is perpendicular to the line direction. So line is vertical. So this will be edge. DE is edge, EF is screw, FG is edge, SE. Option 1. Let's see if here it's correct. Yeah, matching. Hmm. Next question. The theoretical atomic strength of steel has a value of this GPa. We have to calculate the theoretical atomic strength. We are given with E, elastic modulus, mu, surface energy, and the interatomic distance between the atoms in unstrained state. That is the hmm, atomic spacing 2.5 angstroms. Hmm. So, sir has already derived this. The stress varies sinusoidally as you try to move the atoms to break it off, and the highest stress is in between. Let me just draw it here. This is answer number 6. So you have atoms here like this, all are bonded. And this will hmm, this will try to break. So it will be like this. This will break. This will form. Hmm, as it moves in this direction, and this will have a stress associated with moving, and this sigma stress required to move it, sigma max, will be the strength of the material, because if you supply a stress more than that, then the material will deform, and this has been already derived. It will be here. Hmm. So sigma and mu are given. We'll have to see in the lectures what is the relationship. Let me, if any of you know, you can say it out. That will save some time. And let me look at the lecture. So sigma theoretical, the theoretical strength as per the calculation, like the derivation, is equal to E mu by B It depends on the surface energy getting created when the atoms move with respect to each other, or one portion of the material moves. Two surfaces get created. This is the surface energy mu associated with it. B is the Borges vector, E is the elastic modulus. So let us now calculate the value. So I'll have to say that to know the theoretical strength, you need to know the fundamental properties such as the surface energy of the material for that particular plane where shearing is happening. Then only you can tell the strength. Or maybe if you know strength, you can find the surface energy. So let's quickly calculate. 210 GPa into 1.5 joules per meter square. All are SI, so I'm not mentioning units. Into 1.5 divided by B is 2.48 into 10 raised to minus 10, because it is in angstrom. So this will be equal to, this will be very high. It will be equal to, let me do the calculation, 210 into 1.5 by 2.48. Okay, sorry, there's, the formula is slightly different. We have a square root also here. Now it makes sense. This raised to 1 by 2. Otherwise, it will be very high. Equal to 11.3. Sorry, it will be equal to 30 coming out to be, if I put the units also, 35.6 GPA. Uh, yes, matching. I'll suggest that you see how it is derived, so you have a grasp of physically what is happening when you are checking the strength or fracturing the material. And then you need not remember the formula if you know how it came about. Physical understanding is very important. At least in mechanics, it is very important. In an FCC crystal, the following kind of atom displacements can be observed: full slip dislocation, tank partial dislocation, Shockley partial dislocation, and stair rod dislocation. Based on energy considerations, specify which kind of dislocation has the lowest energy and is energetically favorable as compared to others. So, lowest energy and is energetically favorable. Let's see each of them. So we know as energy of dislocation is proportional to square of the Burgers vector magnitude. Planck partial will be equal to by 4 actually. So a square by 2. A square into 3 by 3 square. So I am adding up the squares of the components to know the moduli. Let me just write down the steps in case someone has an issue. Next, let's look at Shockley. E Shockley equal to, you have two dislocations, B1 and B2. Let's look at the sum of squares of both. Be a square by 6 into 1 square plus 2 square plus 1 square into 2, because two different dislocations having the same Burgers vector magnitude. B1 and B2 have it same, equal to a square by 6 square, yeah, by 3. E stair rod is a, okay, this is also a special kind of dislocation, I guess, equal to a square into 2 by 6 square equal to a square by 18. So lowest energy is stair rod D. Frank partial and Shockley have similar. Full dislocation has the highest. Hmm. Next, look at question number 8. Which configuration would align to form a low angle grain boundary? Good question. We have already seen which portions will be attractive, which will be repulsive. So the if this is x, y, Bajaj vector is along x, and dislocation line is along z, then this portion is repulsive. This is repulsive. The rest on this plane is attractive. So this one will be the right answer because the shear stress due to dislocation at the center, this one will cause the other dislocation to move towards the uh, same uh, YZ plane as the first dislocation. So it will move along x and it will pile up. These two, here you have x equal to y, or magnitude x equal to magnitude of y, tau on the dislocation will be 0. So this is a metastable kind of state, you can say. It will not move. Let's check out the answer. It's B. Here it is staircase. Yeah. Last question. Which of the following statements is not correct? True dislocations are not involved in volume change. The stress field increases as we go near the dislocation core. Region of an edge dislocation with extra plane of atom experiences tensile stress, while those below the half plane experience compressive stress. Stress field around edge dislocation is not symmetric, while screw dislocations have symmetric radial stress field. Hmm. Let's look one by one. Screw dislocations are not involved in volume change. In general, dislocations do not cause volume change, like because just extra plane of atoms, which is causing some strain above and below the line of dislocation. So we can say that it is not involved. Stress field increases as we go to the dislocation core. Yes, the closer you go to the dislocation, yeah, to the dislocation core, the more is the stress field due to the, because the dislocation is nothing but a kind of distortion in the material, uh, mismatch in the material, which is associated with bond lengths, which are different from the equilibrium value. Because of that only there are certain stresses which are occurring around it. So it will increase, and we also know the we sir has already derived what will be the value of the stresses as you go away from the material, away from the center. Let me just quickly check if I have written it in my summary. Maybe I haven't. Will be here. Ah, tau equal to minus gp by 2 pi r. So shear stresses change as 1 by r. The higher the value of r, the smaller is the stress. So it's inversely proportional. Then region above edge dislocation, region with extra plane experiences tensile stress. No. Below half plane experiences compressive stress. No, because if you have this kind of a extra half plane, you need to draw this well to understand. If you have these planes, there is this extra plane in between. Then because of this, there will be slight stretching of bonds around it, around this line, dislocation line. And here they, here there will be slight, here the bonds will be slightly closer to each other compared to the equilibrium value, and here will be slightly farther than the equilibrium value. This drawing is also not good actually, not at all to scale, but I hope you get the gist. You can see the you can see the actual images for better understanding. But here you will have let's just quantify. Let's call this a extra above, a above and a below, where a is your bond spacing. So a equilibrium will be more than a below but less than because a below is stretched, so it will be higher than a equilibrium. A above is not stretched, so it will be lower than a equilibrium. So above you will have uh, compression, since the bonds are trying to, since there is too much of packing, so atoms are trying to move away from each other. They are facing a compressive stress. Below they are facing tensile stress. They are trying to come closer. So above they are trying to repel, you can say, and here they are trying to attract. I hope now it is clear why this is false. Third statement. Fourth statement is, as dislocation has symmetric stress field, uh, screw dislocation has it does not have symmetric stress field. Screw has a symmetric radial stress field. This is true. Screw only has a shear stress field and it is symmetric. Circular symmetry. Edge does not have symmetry. It is more complex. So answer is true, false, true, false. We have to find the false one. So it's answer 3. Option 3. With that, the assignment 3 is finished. I'll upload the solution, and if there are no other questions, we'll meet in the next session next Tuesday and discuss week 4's content. Thank you. Goodbye.